Welcome to the last talk. As indicated by the title, the aim of this talk is to see how using computer and more precisely the computer algebra system Macaulay 2, we can do some computation which can help us in our research. In this first part, I will give some introduction to Macaulay 2, I will give some basic comments that we can use. And in the second part, on Wednesday, we will see how we can use Macaulay 2 in our actual research. Macaulay 2 is a free-source computer algebra system, which was created by Liaison and Michael Stillman, with basic packages which are related to the computation in commutative algebra and algebraic geometry. But the system has also been extended by a large number of packages by many people. And also there is a journal which is related to the development of this kind of packages. It is called Journal of Software for Algebra and Geometry, and has published numerous packages and programs for Macaulay 2. You can try online Macaulay 2 using this web page. And the main source of the information, in the sense that you can find many things for computation using Macaulay 2 there, is the web page, is this web page. Also, as I said before, it's a free source program, so you can easily install it in your computer and use it. To start Macaulay 2 on a Unix system or Linux, we type M2 at the command line, and then something like that will appear, which says that you are using Macaulay 2 with the specific version. And here are written the basic packages, okay, that are used for elementary computations, not elementary, for computations in algebraic geometry and commutative algebra. After that, you can see I1. I1 is a prompt. And in order to start computing with Macaulay 2, the first thing that we should do is to define a field. So we choose, for example, field zeta over 101. We denote by KK, we name the field. And it says that, yes, we have a quotient ring. If we want to define a polynomial ring over the field K in 4 variables, we should first denote the variables in a specific way. The variables x1 up to x4, using the standard mathematical notation. This is another very good feature for Macaulay 2, that many of the comments that we use in order to compute are related with the mathematical notions, so it's easy to interpret it. So we name the polynomial ring by R, equal to K, the field that we defined before, and we know the variables x1 up to x4. And Macaulay 2 recognize that this is a polynomial ring. Now, if we want a specific element of the ring, that, we use the index notation in order to obtain it. If we want the 0 element, we write down 0, underscore, and the name of the ring. You can use, of course, another name for the ring. You can call it S or whatever you prefer. Okay. And this is for this the 0 element. And this from here says that we are in the ring R. This notation is useful when we have many lists. For example, for some reasons, maybe we want to introduce more than one list. By discrete, you know every time in which list you are working on. Okay? If we are interested for the unit of the entire, we write it in 1_ and the name of the ring, and this says that we have this unit in the entire. If we want to write in 103 in the entire, which produces 2 because we are working over the ring modulo 101. Okay? Our field is Z over 101. Is it clear so far? Do you have any questions? Basically, just elements of the ring. Okay. We can also use Macaulay-2 in order to obtain a random homogeneous element of degree I. How we can do it? We write random. By I, we know the degree that we are interested, and by R, and after that, comma, R, the ring that we are looking for. So random 0, 1, which returns as a constant. If we use random 1R, we take a random linear element of the ring. And we can continue this process. We can ask about random 2R, 3R, whatever we need. Okay. Also, using Macaulay-2, we can compute the basis of the subspace of ring elements of a given degree by writing basis, the word basis, parenthesis I, which is the degree that we are interested in, comma, name of the ring. So if we want an element, a basis of the first plane piece of part, we write basis 1, comma, the name of the ring. And it says that we are working on polynomial with 4 variables, so we produce x1, x2, x3, x4 as a basis in a matrix form. Okay. If we want the basis for the second graded piece, we write again basis 2, where this is for basis of the basis for the basis of the second graded piece of part, and the name of the ring. So this produces this matrix, which are all monomials of degree 2 and the variables x1 up to x4, which is the right thing. Also, we can compute the Hilbert series of the ring by using the command Hilbert series. Here is a capital S, we should take care of it. And the Hilbert series of the polynomial ring is the polynomial ring is 1 over 1 minus p up to 4. Now, if we want to write down an idea, to define an idea, we use the function idea. So you see, it's related very much with the mathematical notion that we use. Here we define the Stanley-Rising ideal of the Fordham. So we use idea and we write down the generators, and that's it. this produces an ideal which says that belongs to ideal to the ring R. Okay. And we denote this ideal by R. It is very useful to use names about what we are defining because sometimes we want to recall it in order to do some operations or to compute something. So we should give names on what we compute. We define J to be the ideal X1. And now we can ask many questions related to our idea. The first question is if our ideal is homogeneous. How we can do it? We write is homogeneous and the name of the ideal that we want to check if it is homogeneous. Here we are using for ideal I, which says that yes, it's a homogeneous ideal, which is true because it generates the elements of degree 2. After that, we can ask if our ideal is prime by using the command is prime. So here is prime, again the name of the ideal, which produces that it is false. The standard ideal performance is not a prime ideal, obviously. Are there any questions? Then we should, maybe we want to check about the codimension of an ideal. We use the command codi, and again the name of the ideal. So it says that I is a codimension 2 ideal. And if we want, if we want to work with modules, so we have an ideal and we want to construct the quotient module, we can use this command, which is the name of the ring, cap1, with this simple Macaulay to understand that we are talking about modules, not just rings or ideas. Modulo, the name of the ideal. So if we want to construct the model which is related to the ideal I, R1 over I, which produces that this is this quotient, this are model, which is quotient of R1. Instead, it says which structure we work. Also, we can compute the minimal graded free resolution of the quotient, and this is given by using the command res. So we name this resolution C be equal to res and the name of idea, res I. And it gives us a chain complex of this form. And if we are wondering which are the differentials in this chain complex, can be computed by taking the name of the resolution. Here I denote it by C, so C point DE underscore, and with this we denote the position that we are interested in the resolution. So C DE 0 is 0. CDD1 returns back the generator ideal. CDD2 gives this matrix. And we know that this is the right thing because it's a complete section and the minimal resolution is related to that is a causal. So we can check in this example that this is the right thing. And CDD3 of course is equal to 0. Okay. Now we can use Betty in order to compute the Betty table of the resolution. and see the degrees of components by typing Betty and the name of the resolution. So here we have Betty C, which give us these metrics. And from this matrix, we can see many things. For example, this index here says that we have two generators of degree 2. And also we can use this matrix in order to decide if the ideal that we have, if the link that we have is Gorenstein. Before we compute the codimension, we have a codimension 2 idea. So the first thing that we should check in order to see if it is Gorenstein is if it is Cohen-Macaulay. And it is Cohen-Macaulay because here, if you see, the length is equal to 2. It's equal to codimension. In other words, we can compute the projective dimension using the length in this set. And also, in order to check if it is a Gorenstein complex, now we know what's Cohen-Macaulay, so the next step is to go to this last column. And if in this last column there is only one non-zero element which is equal to 1, then taking into account that we have checked that it's Cohen-Macaulay, we know that this is a Gorenstein here. And this is an important information, especially when you are working with Gorenstein rings, when you want to check if you have a Gorenstein ring of higher codimension with many generators. Okay. Now, if we want to construct the quotient ring, we use this command, the name of the ring over the name of idea. It is important to distinguish it from the previous command, but we don't have one here. It's just the name of the ring modulo of the idea, which produces this quotient. And using the command D and the name of the ring, the quotient ring, we can compute which is what is the full dimension of this ring. Are there any questions so far? Another question that we may have is if we have a given ideal, which are the associated primes of R? We can use the command as in order to compute the associated primes of a given ideal. So as and the name of the ideal, and we see that the associated primes of the Stanley-Reisner ideal corresponding to foregoing are these 4 components. Also, Macaulay 2 can give us the minimal set of generators of an ideal by using mean gens and the name of ideal. So mean gen psi produces this metric, which is the minimal set of generators for the Stanley-Reisner ring of the foregoing. And if we are wondering about algebraic operations for ideals, Macaulay 2 can also do it. If we have 2 ideals, I and j, we can take the sum of ideals by using I plus j, which gives this ideal. We can compute the intersection by using the command intersect and the names of ideals that we want to compute the intersection, and says that this is the ideal with these generators. We can compute the product of 2 ideals by using I star j. The colon ideal that we discussed before I take I colon J. And if we go back to the first lecture today, this returns the idea, the Stanley-Reisner ideal of the star. Okay, because G is ideal x1, which corresponds to the vertex 1 of the foreground. And by computing the column ideal, we have the ideal of the star. And the next command here computes the ideal of the lead. So we first take the column ideal plus the ideal which corresponds to the vertex 1. So we use elementary operations in order to have the Stanley-Reisner rings of star and link, which can be really tricky if you try to compute it by hand, for example. Also, using Macaulay 2, if you have done a computation, you're not sure about the result, you can just take it using the computer. Okay. We can also compute the radical of an ideal by writing radical and the name of ideal. And it says that the radical of I, it says that the radical of I is the original ideal. So we have that for the case of foregone, the Stanley-Reisner ideal is radical. Also, we can check if we have two ideals, if the one ideal is contained to the other by using the command is subset and the name of the ideals. And it says that the ideal I, it is not contained in the ideal J, it returns false. Okay. Now we will denote by I the ideal which is generated by 2 degree 1 elements. So we use I in. Oh. We use I in be equal to ideal, and we take random 1R twice in order to have the ideal of 2 linear elements. And we can define the Artinian reduction, R over I plus I lin, and we can compute the dimension, and it says that yes, it's 0 dimensional, so we have an Artinian thing, right? We can compute the dimension of the degree d part of R over I using the command Hilbert function d comma I, where d is the degree. So the Hilbert function of the 0 graded part of R over I is computed by writing Hilbert function, the degree that we are interested, 0 comma I, and says that the 0 graded part of R over I is 1 dimensional. And if we want to compute the dimension of many degrees of R over I, we can use a function which is called apply, which starts from a sequence and a function to specify what to do with each element of the sequence. So here, using apply, and again the Hilbert function command above, we can compute the dimension of degree 0 up to degree 10 parts of R over I. Instead of doing each computation separate for 0, 1, 2, 3, we can do it in once using apply, right? Are there any questions so far? These are some basic commands, some basic things that we want to know if we have a ring and an ideal, which is useful like an alphabet if you're working with commutative algebra. Okay. Now we will talk about a specific package, which is very interesting if you want to do some computations related to simplicial complexes. It is called simplicial complexes package, as indicated by its name. It is related with simplicial complexes. The authors are Sorin Popescu, Gregory Smith, and Mike Stillman. You can see more details about this package following this address. We recall from the morning that the simplicial complex on a set of vertices is a collection of subsets D of these vertices, such that we close undertaking subsets, which means that if F is in D, then every subset of F is also in D. In the following slides, I will try to demonstrate how we can use this package in order to have some computations related to the notions that we discussed in the morning in my talk. Okay. Okay. In Macaulay 2, the vertices are variables in a polynomial ring, and its subset is represented as a product of the corresponding variables. We will work with foregon again, with vertices 1 up to 4. But before we start with the specific example, we should discuss how we can call a specific package. This type of packages are not included in the main thing of Macaulay 2. We should recall it every time that we want to use it. So in order to do it, we type needs package, these symbols, and the name of the package. So in our case, we will type needs package, and the name of the package is simplicial complexes. So we restart the program by using restart, needs package, and the name of the package, simplicial complexes. And it says that, yes, you have called the package. Here it is. Okay. We define again our field and the polynomial ring, as we said before. As the next step, we want to define the phase ideal, also known as Stanley-Reisel ideal. And we can do it using monomial ideal, parentheses, and we write down explicitly the generators of ideal. And it says that we have a monomial ideal with these generators. Is it clear? We start by the phase ideal, and we want to produce the simplicial complex. So we want to put Macaulay 2 to give us back which are the facets. Because, as we said, simplicial complex is completely determined by its facets. So we use the function simplicial complex, we write simplicial complex, and the name of ideal. I give the name foregon because we are working with foregon, and we will use it to compute other things related to that. And it says that you have a simplicial complex, and here are the facets: 1, 2, 2, 3, 1, 4, 3, 4. We can ask about the dimension of the simplicial complex by using the name, by using D and the name of simplicial complex. We are interested for foregone, so we use D, and we write down the word foregone, which produce which give us back 1, and we know that it's true because it's a one-dimensional simplicial complex. So I want to emphasize with the fact that many things that you maybe want to compute by hand, you can do it by using computer. And it is really useful when we have some examples which are really complicated, not just foregone or endless. Okay. We can ask about the I faces of our simplicial complex by using faces, parentheses I, comma D. So for the zero-dimensional faces, we use faces 0, comma, and the name of simplicial complex, which is here foregone, and says that we have 4 zero faces, x1, x2, x3, x4, our vertices. One-dimensional faces are given by typing faces 1 and again the name of simplicial complex. And you can also ask about the facets of a simplicial complex by using the command facets and the name of the simplicial complex. So it says that the facets of the foregone are again 1, 2, 2, 3, 1, 4, 3, 4. Next step, we want to compute the vector of simplicial complex. So we write a vector and again the name of simplicial complex. We denote it by F, and it gives that the F vector of a foregone is 1, 4, 4. Here is F minus 1. We don't write them. So 4, 4. Yes. We can also ask if a simplicial complex D is pure. We call pure simplicial complex a simplicial complex which all facets have the same dimension. So we ask, is pure and the name of simplicial complex? And it says that yes, it's true, because all the facets are one-dimensional, so they have all the same dimension. After that, maybe we want to compute the Stanley-Reisner ideal of a simplicial complex. In order to do it, we use ideal and the name of our simplicial complex. So it says that if we start by the simplicial complex, the Stanley-Reisner ideal is x1, x3, x2, x4. So if we have a simplicial complex, we can use this command in order to take a Stanley-Reisner ring related to this simplicial complex. And vice versa, if we have the ideal of the face ideal of a simplicial complex, as we discussed before, we can recover what is the simplicial complex. It gives us back the facets. Okay. If we are interested to compute the link and star with respect to a specific phase, we can use the command link the name of simplicial complex, comma, the monomial which correspond to the phase that we want to compute the link with respect to it. So link foregone, the name of simplicial complex, comma x1, and it gives x2, x4. Okay. In a similar way for the star, foregone, comma x1, and it gives 1, 4, 1, 2. Is what we have already computed in the morning. Okay. Okay, and some good references to start with Macaulay 2 is the classical book from Eisenbach, Creation, Stillman, and Strunfels, Commutations in Algebraic Geometry with Macaulay 2. You will find many things that I refer to and much more than that. And also Halseng's book, Computational Algebraic Geometry. This is the book that my supervisor, Professor Papadakis, proposed me in order to start algebraic geometry with combination with Macaulay 2, because I had no idea with the programming and so on. And it was very useful. It was a very good choice. And thank you very much.